Today we're going to be talking about the concepts of linearity and superposition. All right, stop talking. I'm talking now. So superposition is a smaller part of a larger concept called linearity. Okay, so superposition is what is traditionally taught in most circuit analysis textbooks. I'm going to go a little bit beyond that because I think that the concept of linearity can be used as a tool in circuit analysis as well. Okay, so we're going to start with the superposition theorem. I remembered to print my notes. I forgot to actually bring them to class, so I'm going to have to do this a little bit from memory. So this isn't going to be in the nicest speech as ever. But the superposition generally states that for a linear network, so this would be containing, let me rephrase this, fixed value resistors, capacitors, and or inductors. As well as voltage and or current sources. So for a linear network that is excited by multiple independent sources, the response to these inputs will be the same as if the network were excited individually and the results were added together. Okay. So this is a bunch of gobbledygook because again, I forgot my notes so that I could write down the exact thing here. So we are going to kind of figure out what the hell this means in practice. Okay. So let's start by analyzing a circuit. We're going to analyze the circuit multiple times today in a couple of different ways. So let's say that we have an 8-volt source. Let's make this a 10 ohm resistor. Let's make this a 6 ohm resistor. Let's make this 4 ohm resistor. And let's make this a 2 amp current source like so. Okay. So we have a circuit here that is being excited by multiple independent sources, right? There is an independent voltage source on the left-hand side of the circuit. supplying 8 volts, and there's an independent current source on the right-hand side of the circuit supplying 2 amps. Okay, so our first criterion is checked. I'm going to define the response that we're interested in to simply be the current flowing through the 6 ohm resistor, which I'm going to call IX. Okay. So what the superposition theorem states is that if I analyze this circuit with both of these sources on and find IX, I will get the exact same result as if I analyze this circuit with the 8-volt source on by itself, find IX, and then the 2 amp source on by itself, find IX, and then add those 2 results together. So we're going to prove just that by analyzing this circuit with both sources on, and then we're going to reanalyze it using superposition to verify that we get the same results. Okay. So our first method is what I'm going to call the kitchen sink method, because we're just going to throw all of the circuit analysis techniques that we know at it and see what sticks. So I'm going to redraw my circuit. And because we're going to wind up using Kirchhoff's voltage law and Kirchhoff's current law, I'm going to go ahead and define several different things here. Okay. So I'm going to call the voltage drop across the 10 ohm resistor V10, and I am arbitrarily choosing positive polarity on the left. I'm going to call the voltage drop across the 6 ohm resistor V6, arbitrarily making the positive polarity terminal on top. This is going to be the voltage drop across my 4 ohm resistor, positive polarity terminal arbitrarily on the left. I'm going to call this current I10 because it flows through the 10 ohm resistor. The current flowing down through the 6 ohm resistor already has a label IX, so we're going to leave that alone. And I'm going to define my current I4 in this direction so that we can easily see that it's just 2 amps flowing through the 4 ohm resistor. So effectively, every voltage and current in this system has a name at the very least right now. Okay. So in order to solve this system, what I'm going to do is I'm going to apply Kirchhoff's voltage law around the left-hand loop here, right? So KVL around the left-hand loop is going to give me negative 8 volts plus V10 plus V6 is equal to 0. So I currently have one equation and 2 unknowns, so I've got more work to do. I'm going to apply Kirchhoff's current law at the top middle node. So the currents flowing in to that top middle node are I10 and 2 amps, and the current flowing out is IX. And so now I have 2 equations and 4 unknowns. And so what I'm going to do now to relate things to each other is use Ohm's law. Right? Actually, let me do these Ohm's law equations down on the bottom. So I could say that V10 is equal to 10 ohms times I10. I could say that V6 is equal to 6 ohms times IX. And for what it's worth, I could say that V4 is equal to negative 4 ohms times 2 amps. Looks like it'll be negative 8. So I'm now up to 5 total equations, and only 4 unknowns. So I've kind of overspecified things here. So realistically, we're not even going to have to use this guy right here at all for setting up this system, right? So what I'm going to do is I am going to substitute my Ohm's law relationships into this KVL equation. So V10 looks like 10 ohms times I10. V6 looks like 6 ohms times IX. And I'm going to move that 8 volts to the other side of the equal sign so that I get this, right? So 10 ohms times I10 plus 6 ohms times IX is equal to 8 volts. I'm going to rearrange my KCL equation very slightly. So I'm going to say that I10 minus IX is equal to negative 2 amps. Now, we could very easily solve this system of equations by hand, okay? But we are about to reach a point in this class where we're going to be solving systems of equations practically constantly. So I would like for you all to solve your system of equations using your calculator, okay? If you don't know how to solve a system of equations using your calculator, please let me know and I'll come by and try to help you out. Sorry. So set it down. You go to second and then press the tangent button where it says system solver. Okay. This is a 2x2 system, so we're going to use option 1. So let's call our first variable I10 x, our second variable ix will be y. So the coefficient of our first variable is 10. Our coefficient of our second variable is 6. Our constant term is 8. In our second equation, our coefficient for our first variable is 1. Our coefficient for our second variable is negative 1. And our constant term is negative 2. And then we press enter to solve it. All right, thank you. All right, so hopefully those of you that know how to set up a system of equations in your calculator and solve it got these results. Anybody verify this for me? I can't see that far because I'm old. Okay, great. So multiple people got the exact same answer, solving the system of equations. So I feel pretty confident that this is the correct result here. So we can see that with both sources on, the response that we're looking for, the current Ix has a value of 7/4 of an amp, right? So now let's look at this same exact circuit using method number 2, where we employ superposition. So because there are two sources, let me restate that, two independent sources, we're going to wind up analyzing this circuit twice. So the first time, I'm arbitrarily going to choose that my voltage source is on and my current source is off. Okay. So here's my 8-volt source. My 10 ohm resistor, my 6 ohm resistor, my 4 ohm resistor. And now let's talk a little bit about how we turn a current source off. So let me ask you what I hope is a very simple question. What does it mean for the current source to be off? It is not supplying current, or it is supplying exactly 0 amps of current, right? Okay. So what element do we know of that by definition has no current flowing through it? An open circuit. Absolutely right. So to turn off a current source, we replace it with an open circuit, or another way that you could think about it is literally just take it out of the circuit entirely and leave behind that open circuited set of terminals, right? So this open circuit set of terminals here on the right-hand side represents our current source being off. Now I'm going to identify my response, Ix here, and I'm going to call this Ix prime because this is my first iteration of applying superposition, okay? So if I were to analyze this particular circuit, what would Ix prime be? Somebody tell me how to do it. Why has nobody told me how to do it? This should be really easy. Absolutely right. So 8 volts divided by 10 ohms plus 6 ohms. So 8 over 16 seems to me like it's going to be half an amp. Now we're going to analyze the circuit with the voltage source off. And the current source on, okay? So let's talk about how we turn a voltage source off. What does an off voltage source mean? Supplying 0 volts. What is the element that we know of that forces the voltage drop to be 0? A short circuit. So we're going to replace our voltage source with a short circuit or just a wire. Here's our 10 ohm resistor. Here's our 6 ohm resistor. Here's our 4 ohm resistor. Here's our 2 amp current source. And I'm going to call this response Ix double prime because this is our second iteration of applying superposition. Okay? So how might I go about finding Ix double prime? So you're halfway there, Christina. So Christina, there we go. So Christina has observed that the 10 ohm resistor and the 6 ohm resistor appear as if they are in parallel. And there is a known amount of current flowing into that parallel network because all 2 amps flows through the 4 ohm resistor before it divides between the 10 and the 6. So this is a perfect place to apply current division. So Ix double prime is going to look like 2 amps. So the resistor we want the current through goes in the numerator, so that's why we have 1/6 ohms there. In the denominator, we're going to have the resistances that are in parallel, so that's going to be 1/6 ohms plus 1/10 ohms. So that I don't make any mistakes trying to do this in my head, I'm going to throw it in my calculator. So 2 times 1/6 over 1/6 plus 1/10. Comes out to be, I got 5/4. Yeah. Now I'm slightly concerned. So the reason why I'm concerned is I feel pretty strongly that if I add 1/2 and 5/4 together, oh no, I should get 7/4. Okay, yeah. Less concerned, just bad at math. Okay. So IX, the response due to both sources being on, is going to be IX prime plus IX double prime. So 1/4 is the same, excuse me, 1/2 is the same as 2/4 of an amp plus 5/4 of an amp gives us 7/4 of an amp. And this is literally the exact same thing that we got when we analyzed the circuit with both sources on at the same time. Now, I would argue that in this specific instance, the analysis that we're doing by using superposition is significantly easier than the analysis we had to do when both sources were on at the same time. Will not always be true. So this isn't something that you can just apply every time to make things easier, but in some cases, it's going to work out that way. Okay. So this is the superposition principle in action. One, yes.
So, second here's why, so I'm just the reason why.
So we use this equation. So this is the equation that we use for current division. Okay. So current division can be applied whenever a known amount of current is entering into a network containing resistors in parallel. So our network of resistors in parallel is this 10 ohm resistor in parallel with this 6 ohm resistor. And if we follow this 2 amp current around, all of it flows through the 4 ohm resistor. So that's why we have 2 amps of known current dividing between the 10 and the 6. This is a perfect place to apply current. Any other questions about this particular example? All right, so like I said, this is an example of how to apply superposition. One thing that I do want to point out is that we can only turn off independent sources. So a dependent source must always be left on if we have one, okay? All right, so now let's talk about linearity. So this is going to seem like it's an entirely different topic, but I promise you it's actually the same thing that we were just talking about. So for those of you that are in electrical engineering and biomedical engineering, and I believe mechanical engineering, you will sooner rather than later start looking at systems from a different perspective than how we are currently approaching circuits, okay? So we could think of a circuit as a black system, like so. Where on the left-hand side arbitrarily is where we will apply our inputs, whatever they may be. And on the right-hand side will be where we measure our outputs. So for a circuit, on the left-hand side would effectively be like our inputs would be voltage sources, current sources, and things like that. And the outputs that we're measuring are voltages and currents elsewhere in the circuit. For a mechanical system, like let's say an accelerometer or something like that, the input of the system would be acceleration. The output of the system would be the displacement of the mass or something like that that you can measure. Okay, practically any system can be thought of in this particular form. Okay, so typically speaking, if we apply some input, let's call it x1 of t, we can expect the system to give us some output that is associated with that input. Okay. And if we applied a separate input, x2 of t, by itself, we would expect to see a separate output, y2 of t. Well, from the superposition theorem, also known as the additivity property of linearity, if I apply an input of x1 of t plus x2 of t, I will get an output that is y1 plus y2. And we literally just saw things work like this in the circuit that we analyzed. So there's another big part of linearity called homogeneity. And homogeneity is just a fancy term for scaling. And so what the homogeneity principle tells us is that if I scale my input by an arbitrary time invariant factor alpha, my output should scale by that exact same thing. If I scaled my second input by a scaling factor of beta, my output should scale by that exact same amount. So if I apply alpha here and beta here, I should get alpha here and beta here on the output side as well. So let's look at the homogeneity property as applied to the circuit that we were just dealing with. So let's say that I was going to scale both of my inputs by a factor of 2. So that would mean that I would have a 16-volt source on the left-hand side. All of my resistors will be exactly identical as to what they were. 6-ohm resistor here. 4-ohm resistor here. Excuse me, 4-amp source here. Here is my quantity Ix. So if we scaled our inputs by a factor of 2, what should we expect our output to be? So if it was 7/4 before we scaled it, and we're scaling by a factor of 2, what should the output be? 7/2, right? Let's see if it works out this way. So once again, I'm going to call this voltage V10. I'm going to call this voltage V6. I'm going to call this current I10. I'm not going to bother defining things for the 4-ohm resistor because it turns out we don't need it anyway. Applying Kirchhoff's voltage law and Ohm's law simultaneously, we're going to wind up getting 10 ohms times I10 plus 6 ohms times Ix is equal to 16 volts. And when we apply Kirchhoff's current law, at our top middle node and rearranging. So we're going to have I10 flowing in minus IX, because that's flowing out, will be equal to negative 4 amps. If we solve this system using our calculators or by hand, whatever floats your boat, what do we wind up getting? So if you solved it in your calculator, most of the calculators store things. So I'm just literally going to change the constant term for my first equation to 16 and the constant term for my second equation to negative 4. When I solve, I get negative 1/2 of an amp and positive 7/2 of an amp. Exactly what we expected. So this was us just applying the homogeneity or scaling property, right? So we scaled both of our inputs. We found out that the output is just a scaled version of the output from our original circuit. Now let's apply both principles at the same time. So we're going to scale each different source by a different amount, okay? So I want to make a table here really quickly. So I'm going to put inputs on the left-hand side and outputs on the right-hand side. So the first time we worked this circuit, we observed that when we applied 8 volts and 2 amp source, our output was 7/4 of an amp. Then we worked it with just the 8-volt source on, and if I'm not mistaken, we saw that our output was 1/2 an amp. We worked it with just the 2 amp source on. We saw that our output was 5/4 of an amp. And we just worked it a moment ago where we applied twice 8 volts and 2 amps, and we got twice 7/4, which turned out to be 7/2 of an amp. Okay. So let's say that this time I scale my voltage by a factor of 2.5. So 2.5 times the 8-volt. And then let's scale the current by a factor of -3. What we should expect to see is 2.5 times 1/2 an amp plus -3 times 5/4 of an amp. Let me add all that stuff together. -2.5 amps. So I have a prediction for what the current flowing through this particular resistor is in this circuit without doing any circuit analysis whatsoever, just using the additivity or superposition principle and the homogeneity or scaling principle of linearity. So if we were to analyze this circuit, so what's 2.5 times 8? 20, right? -3 times 2, so that's just going to be a 6 amp current source direction down. Here's IX. Let me define, give me V10, V6, I10 like so. Applying Kirchhoff's voltage law, we're going to get 10 ohms times I10 plus 6 ohms times Ix is equal to 20 volts. Applying Kirchhoff's current law, we're going to have I10 minus Ix is equal to positive 6 amps. Solving this system, what are we going to get? Excuse me, what are we going to get? So let's throw it into our system solver real quick. So I'm going to change that to 20, change that to positive 6. I get 7/2 of an amp for I10 and negative 5/2 of an amp for Ix. Well, negative 5/2 is the exact same thing as a negative 2. Right? So why linearity can be so great is because it allows us to predict how the circuit is going to behave depending on how it predicted for other things. So effectively, it means that any voltage source, the value of it or the value of any current source is completely and utterly arbitrary. Because if we know how the system behaves for an input voltage of 3 volts, we know how it behaves for any input voltage. If we know how the system behaves for an input current of 5 amps, we know how it behaves for any input current. And then if we want to see what happens when we combine those together, we can just take the individual results and add them together. So it can be an extraordinarily powerful tool to apply for circuit analysis, particularly in very difficult. All right, so that is enough ranting out of me. I do want to point a couple of things out here. So first, let's look at the web work assignments, because I'm going to tell you something a little crazy. So this should be homework set number 5. All right, so for this first one, problem 1 has absolutely nothing to do with superposition. Okay, so let's just start there. Number 1 has nothing to do with superposition whatsoever. Problem 2 here is a great place to apply the scaling principle of superposition. So in part A, you're asked to solve for Vs if Ix has some particular value. And in part B, you're asked to solve for Ix if Vs has some particular value. You really only need to solve one of those, and then you can use the scaling principle of linearity to figure out what the answer to the other thing is. Because once you know how the system behaves to an input, you can scale that input by any amount to match the other thing there, right? So there's no need whatsoever to analyze this circuit twice, once forward and once backward. Solve A or B, and then from there, you should be able to get the other answer just by doing simple math, okay? No circuit analysis whatsoever. For problem 3, part A is a great practice problem for superposition that will also help to reinforce the concepts of voltage and current division. Okay. Parts B and C are hot garbage for superposition. And the reason why I say that is because even using superposition, you're going to wind up having to set up a system of equations in order to solve these things. And our next 2 class meetings are on nodal analysis and mesh analysis, respectively, which are literally just master classes on setting up systems of equations to solve circuits. So it will literally save you time and mental energy and effort if you just don't do part B and C yet and save them until after we learn nodal analysis on Friday. Once you learn nodal analysis, you can do each of these things in about 2 minutes a pop. If you do them, try to use superposition, expect 20 to 30 minutes per. So it's just not worth your time. Not saying it can't be done, absolutely can. It's just not a good use of your time. When we look at problem 4 here, this is a great place to actually apply superposition, and it is the last problem in the set. So problem 2 is all about, in my opinion, using the scaling property of linearity. Problem 3A is a great place to practice superposition as well as current and voltage division. 3B and 3C, wait until you learn nodal analysis to save yourself the headache. Problem 4 here, great for superposition. All right. So the last thing that I want to bring up here is the in-class assignment. Because I want to kind of explain what my expectations are for this particular in-class assignment. All right, so here we have our in-class assignment. It's only a single problem because there used to be a lab after this lecture, but I started reorganizing the labs to actually coincide with the topics we were talking about. But anyway, so in part A here, you're asked to determine the contribution of the 1 amp current source to the voltage Vx. So the input that you're leaving on is the 1 amp source. You're turning off the 5-volt source and you're solving for Vx, okay? That's how things are going to be phrased on your exams as well. I want the contribution of a particular source to a particular quantity, screams superposition. It is practically the only types of problems on the exam that will tell you how they're supposed to be solved, okay? And if you've looked at any of the previous exams, you'll see that. For part B, you want to determine the contribution of the 5-volt source to the voltage Vx, which means you leave the 5-volt source on, turn the 1 amp source off, solve for the quantity Vx. Part C says using the results of parts A and B, determine the voltage Vx with both sources on. I'm expecting you to do no circuit analysis whatsoever here, literally just add the results of A and B. For part D, we are scaling sources, right? So if the voltage source were replaced with a 3-volt source, that's the same thing as scaling that 5-volt source by a factor of 0.6. Positive polarity on bottom, so actually it's scaling it by a factor of negative 0.6. And the current source were replaced with a 2.5 amp source direction up, so that one's being scaled by a factor of 2.5. Use the properties of linearity to determine the values of Vx. So effectively, you should be able to multiply the result of part A by a factor of 2.5, multiply the result of part B by a factor of negative 0.6, add those results together and come up with part D. No circuit analysis necessary whatsoever. That's the beauty of linearity. All right. So that's enough ranting out of me for today. If you have any questions, I would be more than happy to answer them. If not, have fun, as much fun as you can, working on your in-class assignment. Yes, sir.
That's just the last problem.
The web work that's due today, the last problem. What
Yes.
web work is due today?
The web step 4. I think everybody has this problem.
All right,
Everybody's-
homework set number 4.
Okay.
Problem 5. All right, so I've been asked to work this particular problem or help you guys work this particular problem for your homework set. So let's take a quick stab at that really quickly for those of you that want to pay attention. See. All right, so this is the circuit for homework set number 4, problem, whatever the last problem is, okay? So the first thing that I'm going to do is I'm going to identify all of my different nodes. So I'm going to use different colors. So this big honking guy here is one node. This big honking guy here is one node. We have a node here. And we have a node here. So the first thing that I can see just by looking at this thing is that the resistor R1 and the resistor R2 are in parallel with each other. And I can see that because they both share the red node and they both share the green node, right? So what I'm going to do is I'm going to erase both of those resistors, take them out of the circuit, and replace them with a single equivalent resistance between the red node and the green node. So get rid of this guy, get rid of this guy. And now I have an equivalent resistance of, let's call it REQ1, where I'm going to write out over here, REQ1 is R1 times R2 over R1 plus R2. I can do something similar for resistors R3 and R4, right? They are in parallel because they share the blue node and they share the purple node. So let's erase these guys like so. Where REQ2 is R3 times R4 over R3 plus R4. Well, now I can obviously see that the 100 ohm resistor is in series with REQ1. So I'm going to call that REQ1 prime is just 100 ohms plus REQ1. And I'm going to call REQ2 prime as the 250 ohms in series with REQ2. All right, so now this is a single node pair circuit. I have 3 current sources in parallel. So I am going to just arbitrarily choose that I want my direction of my equivalent current source to be to the right. So that means I'm going to have I1 plus I3 minus I2. And then these 2 current sources are going to go away. Too far. Like so. And now, using current division, I could say that IX is negative I1 plus I3 minus I2 times 1 over REQ2 prime divided by 1 over REQ1 prime plus 1 over REQ2 prime. And Vx is just going to be IX times REQ 2 prime. That's one way to go about it, or I can go the other way around. I could say that Vx is going to be negative I1 plus I3 minus I2, my equivalent current, times REQ 1 prime in parallel with REQ 2 prime. And then once I know Vx, I can say that Ix is simply Vx divided by REQ 2 prime. Whatever way floats your boat. You want to do current division and then Ohm's law, or Ohm's law and then Ohm's law. Is that a sufficient explanation? Anything not make sense? Right, so because I had current sources in parallel, I can combine them into a single equivalent current source, which is just making things look a little neater. Yeah. Yes, exactly right. Specifically because they were in parallel, was I able to combine them into a single equivalent current. Yes, Isaiah. So the negative here is because this current direction to the right is what's splitting up between these two paths. Okay. So based on how we defined current division, we would expect this current to split. Some of it's going to split this way. Some of it is going to split this way. This Ix is in the opposite direction. So we need the negative sign. That's also kind of the reason for this negative sign right here, right? So if we consider Vx negative polarity on the right to be the voltage drop across all of these elements in parallel, this current is flowing into the negative polarity terminal when it hits those resistors. So that's why we get the negative sign right here. And then these two resistors are just in parallel. So it's just total current times total resistance in parallel gives you the voltage drop over everything.